This conference will now be recorded.
Great. So, okay, so welcome everyone. We will have today a talk about by Xona about LEO satellites for time synchronization. I'd like to welcome Dr. Tyler. Dr. Tyler is a co-founder and the CTO of Xona Space Systems. Previously, Tyler worked as a research engineer at Ford Motor Company in localization and mapping group for self-driving cars. He has also worked as a software engineer at Google and as a lecturer at Stanford University, where he co-taught the GPS course. He's also a recipient of the RTCA Jackson Award. Dr. Reed received his PhD in 2017 and master in 2012 in aeronautics and astronautics from Stanford University, where he worked in the GPS research lab. So, with no further ado, I'll make you an organizer. Tyler, the floor is yours.
Hear me all right? Let's see if I can pass the other test and share my screen.
Yeah.
All right. Okay, just present here. All right, I think we have. Perfect. All right, thank you so much. Yeah, thank you, Ahmad, for the kind introduction, and thank you for the invitation to speak here today. It really is an honor to be here with all of you, and it's a really great forum, so we're really pleased to be a part of it. Today, I'm excited to talk about our company, Xona Space Systems, and our vision for commercial navigation satellites to provide position, navigation, and timing services, and the potential benefits we think this can bring specifically to the timing world with a focus on the OCP tab here today. So our company, Xona Space Systems, was founded in 2019 around the idea really that modern technology should be accessible by anyone, anywhere on the planet, in every small town and every small community. Xona was founded by a group of 8 people coming from experience, particularly in the space industry from places like SpaceX and Maxar, but also folks coming from the GNSS world, specifically from the GPS research group at Stanford University, which is where I received my training. We're now a venture-backed seed stage company, just under 30 people. We're focused on building, commercial navigation satellites and really trying to change the paradigm that, navigation satellite systems like GPS, Galileo, GLONASS, and Beidou can really only be built by government superpowers. And really that the time is now for commercialization to provide new capability to keep up with the pace of commercial demand. So you can think of this as, similar to the way that, communication satellites and the Earth observation satellites have moved from government world to the sort of commercial world, really bringing that now from the satellite navigation perspective as well. And although founded around the idea of supporting position and navigation specifically to support autonomy and autonomous systems, for example, I was working in the autonomous vehicle group at Ford Motor Company prior to Xona. We really have come to learn of the benefits of such a system to supporting really the T part of PNT, really for timing. And of course, we have expanded our team in that regard as well with the expertise of Jaime Jaramillo, who brings a wealth of expertise and knowledge in this domain and who's connected us to this group here today. So thank you, Jaime, for that. In terms of geography, we have a presence in the US, Canada, and UK. I'm actually speaking from our office in Vancouver in British Columbia. Our R&D and prototyping lab is in the US, mainly in Silicon Valley area in San Mateo. Our European operations are based in the UK out of London. And to give a picture of the presentation roadmap, we have split this up into 4 major sections. The first is, really what are the needs in navigation and timing, and what are the as far as they go today, and then what are the challenges in meeting those needs with satellite navigation as it exists in its current state. Next is, given those user needs, how might you architect a satellite navigation system, particularly for commercial users in today's aerospace ecosystem, and really have a focus again on those commercial users versus the government approach that has been taken sort of in the past by these other systems. And then in our view, we think this can bring a lot of benefit to things like the OCP tab and the timing community. But of course, we welcome your input as well. We're here to learn, and that's a big part of why we're here today, is to get this great audience and get your feedback. And finally, in the fourth one is, how might Xona services be integrated to support this platform in the future? And so to begin with the first one, I'd love to start with a look at navigation and timing and history. I think I'm very much a kind of history guy, so I'd love to look at sort of where we've come from to get an idea of where we're going. And admittedly, this chart was made from a positioning point of view, but I've also indicated many of the timing requirements that have come out of these systems over the years. And historically, new technologies and modes of transportation brought position, navigation, and timing challenges with them, resulting in many new technologies to support them. 100 years ago, maritime navigation made use of the stars, essentially, which gave rise to kilometers level of accuracy. But as many as you know well, longitude was famously solved by Harrison with precision mechanical clocks, needing seconds of accuracy to get to that level of east-west accuracy, in addition to that north-south that was coming from the stars. 30 years later, in World War II, we see the advent of radio navigation to support aviation, giving hundreds of meters of accuracy. And Loran was later shown capable of supporting time transfer to kind of the hundreds of nanosecond level in certain conditions over the land. 30 years after that, we see...
Excuse me, are you related to Xona Partners?
To Xona Partners?
Yeah.
We're Xona Space Systems. Maybe not familiar with Xona Partners, but yeah, I'm not sure if that answers your question. I guess what do the folks at Xona Partners do? Excuse my ignorance there.
It's a consulting firm.
I see. I see. No, we're separate from that. Yeah.
Okay, thank you.
Yeah, thanks for the question. Yeah, so to really reiterate, we're a startup sort of based primarily in the US with a presence in Canada and the UK. We're focused on technology development of sort of commercial navigation satellites. Yeah, so we're not a consulting firm. We're really very much mission oriented in sort of building that system, which I'll talk more about later in this presentation. Yeah, but thanks for the clarification there. So yeah, 30 years after that, we see the first satellite navigation systems to support the Cold War. This relied through the sort of format of transit. This relied on Doppler shift observation, hence not so much absolute time, but more sort of relative time and sort of calculating those positions, but nonetheless was known capable of doing sort of tens of microsecond time transfer. And of course, now we all enjoy meter level location thanks to GNSS, and of course that comes at the sort of 10 nanosecond level. But the question really is what's next? And the reason for choosing this 30 centimeter point on the chart here is that it really follows the natural progression in terms of desired location accuracy. And when you scale that by the speed of light, that really comes to this nanosecond or better level timing. And to really show that this really has this larger trend, there really is kind of a Moore's law of navigation, where we see every 30 years there's approximately a 10 times improvement in largely available location accuracy. It also suggests that every 30 years there's investment in new infrastructure that was driven by a need, and where we saw that need not only in position but also in the timing domain as well. And so the question is, moving forward, where is that need today in terms of the navigation side? Well, in our view, really, this is intelligent transportation systems. They're really pushing for decimeter or better performance. And satellite navigation holds a lot of potential as a ubiquitous solution to support all forms of autonomy, whether it be land, sea, or air. And an important aspect here is really a common reference, both for position and for timing, because as these systems must ultimately work together and share data between them, they must share that common reference frame to interoperate. Satellite navigation really offers that common advantage at this world scale. Now, there's no official standards out there for localization in this sort of autonomous driving domain, but right now the work from Ford Motor Company indicates that 10 centimeters positioning is most likely what's going to be needed to solve this problem. And the hard part is that's sort of the 2 sigma requirement, but what are the requirements sort of at the 6 sigma numbers, because this is a safety critical system. Well, this turns out to be at that 30 centimeter number. So it really is kind of following that kind of Moore's law of navigation type, that type trend. And decimeter positioning is needed to maintain the vehicle in its lane, but timing is also critically important, not just for the sensor fusion aspect of the system, but also for the information sharing aspect of the system. Because once you're at highway speeds, really, milliseconds are centimeters, and so this really comes down to some pretty tight requirements in that when you're talking about doing the sensor fusion amongst all these different vehicles and different sensors. And to give a point of comparison as to why this is so challenging, it's really that the kind of positioning we're talking about is really unprecedented. In automotive, we're talking about requiring 30 centimeters. Comparing that to aviation or maritime systems, this is really 10 times or 100 times more accurate than what's been required in the past. So this is really the challenge from the navigation perspective. But what about other user groups? I don't mean to focus too much on autonomy here. Which when you look at other user groups in the commercial world, which, by the way, number in the billions when we're talking about GNSS, timing and infrastructure users today are really seeking improved security, improved resilience, and improved indoor capability. There are other users out there as well. The high accuracy position users always want higher accuracy. They're really starting to get down to the desire for single centimeter type positioning numbers, and they want to get those numbers faster and faster all the time. They don't want to wait 30 minutes to get those numbers. They want to get those really in a minute or less. Defense users are always looking for improved anti-jam or anti-spoof capability. Internet of Things users, IoT users are looking for better multipath performance, better indoor capability, lower power at the receiver as well. And of course, automotive users really want all of the above. And generally, this has been our target since the beginning, and really has been what we found is that because those requirements are so stringent, it tends to sort of envelope the sort of other requirements as well. So by targeting really that use case, it really does support all those other use cases as well. But there are challenges in meeting the demands of PNT users out there today. And I think a lot of folks out there, and certainly not folks in this room who know sort of positioning and timing and GPS information, technologies very well. But I think your average person out there, thinks of GPS as just sort of another app that helps you find your way to Starbucks. I think that's most people's experience with GPS out there in the world. But I think what a lot of folks don't realize is how critically reliant our infrastructure is on GPS and GNSS for both position, but also in things like transportation, but more widely for timing in things like telecommunications and things like data center applications, the power grid, sort of synchronization, financial transactions, and of course the list goes on. But despite this reliance, the GPS signal that we do rely on in these applications does have vulnerabilities. For example, it takes less than a 1 watt jammer to disrupt an entire city block of GNSS and sort of provide have sort of denial of service as part of that. And there's a famous example of a truck driver in Newark who had a sort of so-called personal privacy device with them, which is one of these small GPS jamming devices, which unfortunately is very easy to get from places like eBay and Amazon. And unfortunately, it was just trying to protect their privacy, sort of jammed GPS locally to their vehicle, but inadvertently took out, Newark, this sort of local airport that was sort of next to the highway. And so this is the kinds of things that happen accidentally. So you can think of the kinds of things that could happen if folks are actually trying to cause major disruptions. And denial of service is, of course, only one part of the story, because the civil GPS signals that we all rely on really have no encryption or data authentication as part of them. And this makes them very easy to spoof, unfortunately. And to sort of define that spoofing term there, that is to create counterfeit GPS signals to mislead receivers into thinking they are at a different place or a different time, or both than they actually are. And so don't get me wrong, GPS is a phenomenal system. It's a great sort of piece of engineering, and it's what got me sort of interested in this whole domain to begin with. But it really was architected around the user needs of governments and of really a previous generation. And it simply just doesn't meet the demands of emerging technologies that are sort of out there today, and also those that are coming sort of fast on the horizon. And it's just very difficult for those systems to keep up with the pace of the demands of those industries, because there's a lot of resistance to change of those systems, because they're already serving so many users in the billions. There's just a large inertia to change in those systems, which makes sense. But because of these limitations of these systems, and sort of the susceptibility of these signals to things like interference and to spoofing, there's a flurry of new regulations demanding that many of these industries install backups or alternatives to GPS because of this. An example in the United States is Executive Order 13905, which is really targeted at critical infrastructure and sort of mandating that there be alternatives in place to support that critical infrastructure because of that critical reliance on GPS and GNSS. So this sets the stage in terms of the need, but how do we get there? So I'd like to take a look at what's going on in the aerospace industry to better understand its direction as well. So let's start with a look of what's in orbit. And I'm kind of a space nerd, as you've heard from my background, so I'd love to show this picture of the satellites on orbit. And I'll admit that this picture is already some years old now. But this is a look of what the satellites on orbit that sort of are operational around Earth looked like in 2016. And you can see there's some familiar groups that emerge here. There's the low Earth orbit group, which is really very, very close to the Earth, only within a few hundred kilometers or so. And that represented in 2018 about 800 or so of the total 1,400 operational satellites up there. About the other big group is the geostationary satellites. There's about 500 of those, sort of all the way at the outer edge there. And then right in between those two groups is appropriately named medium Earth orbit, and that's where all the navigation satellite systems live in this MEO regime, and there's about 100 or so of them back in 2016. How does this look today and how have things changed? I think sort of that got cut off a little bit on the screen there. But things have changed a lot. There's more than 3 times the number of operational satellites that there was just a few years ago, just over 5 years ago. But the biggest change that we see, you can see that the number of geo satellites is maybe 10% more. The number of MEO satellites has increased, and a lot of that has to do with the completion of the Galileo and Vido constellations. But the big change that we see is really in LEO. We see almost 5 times as many LEO satellites as there was just compared to 5 years ago. And so what's going on in LEO that all these changes have happened? And so it turns out there's many motivations for this, but one is just the increased demand for geospatial data, and the other is an increased demand for connectivity. And in the connectivity side, SpaceX, OneWeb, and others are all building constellations of thousands or even tens of thousands of satellites to provide global broadband. SpaceX, for example, with their Starlink system, has more operational satellites now than there was total operational satellites of all the systems, of all the satellites, of all the governments of the world just 5 years ago. So that's really kind of paradigm shifting numbers. And by the way, they launched 60 satellites at a time, which means 60 satellites is almost the size of the whole Iridium constellation for those of you who are familiar. So it's really, really changing things quite substantially in terms of how people think about space and how people think about satellites and putting things up there. In terms of geospatial data, there's several folks out there doing sort of commercial Earth observation. These are from folks like Planet and Spire, who are providing just really better geospatial data and better view of our planet. And combine these classes of systems or classes of constellations, I should say, represent the so-called mega constellations. And they really represent the new space economy, which is enabled by lower launch costs and new satellite production techniques. So this is building satellites more like you would build a car on a production line rather than kind of more bespoke, individual satellites for specific purposes. And really commercial communications and Earth observation have seen some major disruption in this domain with this new space infrastructure. But we've not yet seen this in the navigation or PNT side of things. And at Xona, we're working on leveraging these new sort of conditions, this ecosystem that has developed around kind of these low Earth orbiting systems to provide new capability in the domain of navigation. And so this is where I'd like to expand into how you might architect a satellite navigation system today, given this ecosystem. And so to give some motivation for this discussion, I'd like to focus on a few requirements and a few differences of the approach typically taken by the sort of government-based GNSS systems. And I'll use GPS as an example just because it was the first and it was sort of architected in a very different time in the sort of 1970s aerospace ecosystem. And compare that to how you might sort of build a commercial system today and how those needs might differ compared to what was used as sort of as the basis of creating the GPS and these other systems. And now this is of course not an extensive list, but just something to highlight some of the differences. First is just the focus on the user group. And so, the kind of GPS system, for example, is very much focused on government use cases, particularly defense and military. But if, thinking of this system here today, really we're going to focus on commercial users and how that might differ, which by the way, commercial users today represent more than 99% of the GNSS users out there today. Next is accuracy. Of course, GPS was famously designed to drop 5 bombs in the same hole. Today, commercial users want to keep the car in their lane. And when we talk about availability, both of course want global performance, but again, commercial users are more focused on population centers. When we come to interference, both are concerned, but one with state level actors and the other with smaller personal privacy devices. And I think most importantly is the user equipment. Commercial users today are really targeted at mass market deployment. And so tables are great, but to give kind of a visual representation of how these motivations resulted in different design decisions and different architectures for these systems, and we'll start with GPS. If we start with that first sort of top level requirement of 5 bombs in the same hole, well, that translates to 10 meter RMS positioning or 30 nanoseconds of time transfer. Next is the positioning technique. A broadcast system is desired because it keeps user equipment simple. It also keeps it stealthy from a defense perspective because you don't have to communicate back to the satellite and sort of radiate energy back to sort of give away your position. It also has this nice feature of supporting an unlimited number of users. Very, very cool feature there. And now we come to some of the perhaps more unfamiliar requirements, which are some of the deeper sort of specific military requirements of the system. And the first one here is just that the space segment has to be radiation hardened to the level of survival of a tactical nuclear strike, which turns out to be very stringent requirements on the radiation hardening of the satellite. It makes it a much more difficult spacecraft to build. To give an idea of how, where this lands on the scale of spacecraft hardening, typically there's from the IEEE, there's a sort of four-level scale of radiation hardening of satellites. And it turns out on that 4-point scale, this represents about 5. So there's a special category, which is category 4A, dedicated to this sort of specific class of hardened satellite. Whereas by comparison, the sort of places where the International Space Station operate, for example, are more of a level 1 radiation environment, and places where a little bit higher, sort of in those higher LEO orbits, are more of a kind of level 2, just to give a point of comparison of how those differ. Another specific sort of military or government requirement is that the system must operate without access to the ground for up to 2 weeks or more in the event that the ground segment is incapacitated, basically during a time of conflict. And this is where the famous, atomic clock requirements come from on those satellites. It comes from the need to maintain that holdover synchronization between those satellites to get that 5 bombs in the same hole, even without the ground sort of being able to sort of update those satellites. And really, this is a strategic requirement from that perspective. Another strategic military requirement was one that sort of required a domestic sort of uplink to the satellites. So that means that the satellites have to pass over sort of the country of origin at least once or more times a day, so that you can sort of command and control that satellite and upload the necessary data to that satellite as well. And so this already rules out orbits like geosynchronous orbit, because those satellites would never pass over certain parts of the world. And so already this starts to constrain where these satellites need to operate. And so you come down to this, so what orbit do you ultimately choose? And the trade-off at the time for GPS was that, well, the satellites had to be radiation hardened, they had to have atomic clocks, and they had to be built in that kind of 1970s or 1980s aerospace ecosystem. And so the result was that medium Earth orbit won over low Earth orbit. And the reason was that the satellites were going to cost about the same because of the other requirements on them. And you needed about 10 times less of them for a medium Earth orbit deployment versus a low Earth orbit deployment. And so launch costs sort of won over build costs. And this is very much the model that's been followed since GPS, and why in many ways the other government systems look very similar. So, Galileo, Xona, Space are all kind of medium Earth orbit systems with similar number of satellites, similar capabilities of those satellites. And often it comes from the fact that the requirements on those systems are very much do what GPS does almost exactly. And so it makes sense that those systems, sort of as a result of that, sort of look very, very similar to it. But for a commercial system, what might you do differently? And you can start by removing some of those specific, government tactical requirements of that system. First, you can leverage things like ground stations as a service. These are players like KSAT, but also places like Amazon, AWS, and Microsoft Cloud Services actually have deployed ground stations as a service to command and control of satellites, pass data between them. So that saves you having to sort of deploy all that infrastructure for a specific constellation building. Sort of leverage some of that existing infrastructure that's already up and running and serving mission critical things already. Next, we assume that these mission critical sort of commercial ground services have very high uptime, so you can remove that sort of longer holdover requirement from the satellite and remove some of the atomic clock requirements from those satellites as well, sort of reducing the sort of cost and complexity of the clocks in the space segment. This allows you to move some of those timescales to places like the ground, where it's just less costly, easier to maintain and operate. Next, we can remove the stringent radiation hardening requirement of the satellite, making instead the satellite tolerant to their space environment. And so this, as was mentioned, for something like a low Earth orbiting system, this can be a level 1 or level 2 sort of level of radiation hardening, compared to this kind of level 4A, that's sort of some of the strategic medium Earth orbit systems that are up there. This leads us to the orbit and the selection there. And what we want is, we want to select an orbit that offers, one is, higher receive power to the end user to help us sort of mitigate the threat of interference. This turns out to push us closer to the Earth because we have less path loss and therefore can provide those stronger signals just by the physics of that situation. Next is we want fast geometry change, so we want the satellite to pass overhead more quickly. This has a lot of benefits for things like multipath detection and rejection, and also averaging, because especially for stationary users, the satellites are passing much more quickly over the head, so that sort of short time scale averaging actually can get a lot in that domain. The next, of course, is just we want sort of a low-cost space signal. So something which in today's ecosystem means leveraging the launchers, the satellite components, and the supply chains of those LEO mega constellations. And so both from a performance and economic standpoint, really these factors are pushing us towards a low Earth orbit constellation deployment. And so the result is a commercial satellite navigation constellation in LEO, which is produced from low-cost satellites produced in high volume with largely off-the-shelf space-capable components. And that's not to say that you replace, space components with off-the-shelf components that are built in high volume, just that the kind of ecosystem of these mega constellations has made a healthy supply chain of space-capable components for these regimes. And the key here is really that these new LEO signals that could come from a constellation like this just aren't bound by legacy. And so there can be inclusion of sort of major upgrades to that system, including things like encryption and data authentication for civil users. And an important aspect is that a commercial LEO layer such as this can add capability that can evolve quickly, more on a 5-year timescale, to keep with the pace of commercial demands. And this is a much more difficult thing to do with legacy GNSS services because they're already supporting billions of devices and has just a big inertia to large changes. And so you can see the complementary nature of government MEO systems and commercial LEO PNT systems to provide more targeted, sort of user-specific, and even sort of bolster that sort of capability for the end user in the short term as things evolve in those sort of shorter timescales. And so to summarize, commercial LEO navigation system has the opportunity to provide several enhancements to GNSS today. The first is precision. And so this faster motion across the sky, the quick geometry change, gives much in the way of rapid convergence for things like precise point positioning techniques, getting you down, to decimeter level type positioning in minutes instead of, tens of minutes, as was previously the case with, traditional GNSS. This also helps with multipath, as was mentioned, particularly for static users. Next is, improved availability and resilience. And this is just stronger signals and more of them. And so being closer to Earth, you have that opportunity to provide those stronger signals. And last but not least is security. Introducing the signals that are sort of new to the table and that aren't bound by legacy can really, it can include things like data encryption and authentication as part of that. So that's really a big step towards solving that, or else mitigating the threat of spoofing that's there today. And so this is the approach that we're taking at Xona Space Systems, where we're building a constellation of 300 low Earth orbiting small satellites that are dedicated to position navigation and timing services. We really are trying to challenge the assumption that satellites in the space segment are outside of the reach of commercial entities. And so our service is known as Pulsar and is being designed to provide highly accurate, secure, and resilient signals in a service that won't change the form factor of user devices compared to GNSS today. So really not trying to increase the cost and complexity of the end user devices, but to instead increase the capability and offload some of that to the infrastructure side. So by deploying these satellites in that infrastructure, providing a service that can still can sort of give you that increased level of service that folks are looking for today in terms of resilience, in terms of security, in terms of accuracy, while not sort of being more cumbersome on the end user in terms of the equipment that's required to get there. Now, of course, building such a system doesn't happen overnight. We have a staged rollout plan with different levels of service planned along the way. Phase 1 is a deployment of 36 satellites. This offers a one-in-view GNSS enhancement service, particularly over population centers. In addition to GNSS corrections, this also brings an additional ranging signal that is resilient and secure. But perhaps most importantly, this also already brings time transfer for stationary users, which can already address many of the challenges for the critical infrastructure side of things. And on that last point, we actually have an engagement with NIST to evaluate the time transfer capability of our demonstration satellites in a cooperative research agreement. Our first satellite is slated for launch in June of this year, so within about 6 months from now, which I'll speak more to in some slides coming up. Phase 2 is the 66 satellites, so this is just adding more satellites to the phase 1 deployment. This fills in some of the gaps over the poles in the equator and brings more satellites in view over mid-latitudes. And these are all stepping stones towards the phase 3 deployment, which is a 276 satellite constellation, which gives really global GPS level satellite visibility and geometry and the full PNT services that are precise and secure. In terms of milestones that we've achieved so far in our general timeline, in the last 2 years, we've built our satellite development lab in San Mateo. We've completed field testing of our navigation payload, which is on the ground at Camp Roberts in California as part of their JIFIX exercise. And we are completing assembly of our demo satellite payloads for testing, which are right now we're on the manifest for the launch of those payloads. The first in June of this year and the second in October of this year. And those will be on a SpaceX Falcon 9 rocket. And then soon after that is when we shift gears into the production system for the phase 1 deployment. So I think this sets the stage in terms of the need and Xona's planned deployment of its Pulsar service. And I'd like to spend some time on our view of how this could be useful to the OCP TAP and to the timing community in general. And we've broken this section down to 5 categories. First is resilience, then security, multipath, accuracy, and indoor performance. On the resilience side, and this of course has been identified by many, but GNSS, having its vulnerabilities can act as a single point of failure in some of these systems. And this is a concern, particularly from an interference standpoint. And so to mitigate this particular aspect, the Pulsar signals are designed to be more than 100 times stronger than GNSS today, really greatly reducing the effectiveness of conventional jammers on the market, as well as the susceptibility to other forms of unintentional interference that just sort of are out there. For example, the wrong hard drive in the wrong place at the wrong distance can be a source of interference, or a microwave oven, or things of that nature. Furthermore, Pulsar in the long term is being designed to be GNSS independent, so really enabling continued operation even if there is a GNSS service level outage, so really at the level of the satellites. Next is security, and as we touched on before, the civil GNSS signals that we have access to today are really unencrypted and unauthenticated. And this is just a product of their time, being designed in the 1970s and effectively being unchanged since then. And the result is that today it's possible to create these counterfeit GNSS signals to intentionally mislead GNSS users into thinking they're either at a different place or a different time than they actually are, or both in some combination. And this setup to do this has actually become relatively easy. This once was a very difficult thing to do. It required specialized equipment, a lot of expertise, a lot of experts to pull this off. But now with a laptop and some hobbyist software-defined radios that you can easily get on Amazon, and some open source software from GitHub, you can be up and running in a few minutes and pretty easily create these spoofing signals. And part of the motivation from the community, from the hacker community in putting this together is not so nefarious of a kind of thing. It was more came to do with cheating at smartphone games. And there's the famous one, which is this Pokemon Go game that came out in 2016, which is a location-based smartphone game where you had to sort of actually be out in the physical world to sort of catch these Pokemon. When you put location in the way of the hacker community, they figure out ways to get around it. And unfortunately, the result of this was this sort of easy setup to now do this GPS spoofing to very easily trick smartphones or other devices, anything really that's using GNSS, into thinking that they're into these other places. So it was always interesting to see what comes out of communities you're not expecting. And so Pulsar really aims to be the first fully range encrypted and data authenticated space-based PNT service that's available to the civilian market to mitigate that threat of spoofing. And in our view, the addition of the Pulsar service adds GNSS outage protection and also protection from jamming and spoofing really at the infrastructure level. Next is multipath, which we touched on to some extent already, but the nature of being in low Earth orbit leads to the satellite passing in just a matter of minutes. So we're talking about a pass overhead in about 10 minutes, comparing that to GNSS, which is more of a kind of 4 or 5 hour pass. And this does lead to substantial benefits in multipath detection and exclusion, and also just multipath whitening for stationary users, including increasing that general accuracy. But there's more to the accuracy story in the context, particularly things like data centers. Often GNSS timing in this application comes in at a single point in the building, usually from an antenna on the roof, which then gets distributed via the network. And the result of this is that each piece of equipment in the network, adds to the overall error budget. There can be a stacking effect on those errors, which can just limit the degree to which certain equipment racks can be synchronized even within the same building. Because it's really a challenge to run, multiple antennas and multiple feeds to the roof, and it becomes very cumbersome to do so. And so one feature of the Pulsar service as part of its fundamental design is the ability to penetrate indoors. And it really removes the need for an external antenna, allowing signal reception directly at the rack level individually. And so in our view, this not only creates tighter synchronization capability between the racks in the same data center, but also the potential for improvements across data centers as well. And to dig into accuracy a little bit more, generally Pulsar is being designed to meet what we believe to be some of the most stringent navigation requirements on the horizon, which results in a signal in space user range error budget at the decimeter or better level. And so scaling this by the speed of light, this is where kind of this nanosecond or better level potential lives, at least we believe. And so we really believe that there's a lot that can be done with this kind of signal in the timing community. Now, certainly many nuances in terms of the implications over time transfer, in terms of traceability to UTC, and all those kind of other nuances that come along with that. And this is exactly why we're engaged with NIST to better understand this from a research perspective. We're also very much interested in working with others in the community as well. So we're here to learn, and we'd love to connect if this is something that is of interest to you and to sort of diving more deeply into. And we think there just generally can be many sort of benefits to widespread access to this level of accuracy. Reducing things like risk of exceeding tolerances in larger systems, but also things like relaxing requirements on other components. For example, holdover may be effective with a given oscillator starting from a more accurate set of initial conditions. And there's also, I think, potential to lead to higher data throughput, sort of in the long term when you're talking about larger synchronization potential, across nodes in the network, sort of as these kinds of things move forward as well. And and last but not least is, of course, the indoor signal penetration, which we've touched on to some extent already. This can really, simplify just things like installation and deployment, as well as just the barrier to entry of, getting this kind of capability directly into the rack. And this removes things such as the need for roof access, renting space on the roof, running the cables up to the roof, eliminates, the outdoor antenna installation and maintenance costs. And with the larger constellation deployment, there leads to a very high probability of at least intermittent signal reception indoors, multiple times per day kind of level. And so even with that, we believe that with that kind of connectivity, with that kind of even if only intermittent, can still meet many of the requirements in this kind of use case. And so this brings us to our last section, which is how can Pulsar integrate into the OCP tab. So let's start with the, sorry, I skipped a slide there. Sorry, just jumped ahead on me by accident, my bad. So let's start with the receiver equipment. In the short term, the first step in our planned service rollout is to work with receiver and antenna partners to develop retrofit kits. And so this is an antenna that has built into it a GNSS and Pulsar receiver. So it has that capability built into that antenna. It then serves to sort of convert that into a signal that is ingestible by existing GNSS equipment already installed in a variety of devices, such as the one that we show here. So it really is just sort of a drop-in antenna replacement to get that capability. In the medium term and the longer term, the more efficient thing is to just build the capability directly into the chipset itself. And so we are working with multiple GNSS chipset vendors to integrate the Pulsar capability into their service, into their devices natively. So we are very much acting as a service provider in this case, not trying to be a sort of end user equipment provider, but rather working with those who are already, already have this sort of network of distributing these devices and sort of working with them to integrate the capability into those devices. So in addition to this, particularly for the demonstration satellites in June, we are working to provide an open source receiver software meant to run on an SDR implementation, so a software-defined radio implementation. And this is to act both as a reference implementation for those who are interested in getting into their equipment, but also to get people up and running in the research community as well, because the more feedback we can get with those demonstration satellites, the more eyes and experts on them, just the better the production service will be. And of course, receivers are only one part of the ecosystem. We are also working with antenna vendors as well as GNSS simulator vendors to bring Pulsar capability to those devices as well, to aid both with testing and deployment of the service. So really trying to build an ecosystem of receivers, reference implementations to help receiver vendors, antennas to help with the deployment, and as well as the receivers as well, and also the simulators to help with the receiver development and just with the general testing and deployment of these devices as well. But the first step in all of this really is to launch our demonstration satellites. And the first one is scheduled for launch in June of this year, and we have a follow-on coming in October. And to support this effort, we've been very fortunate to have several great partners and investors such as those listed here. So we're very pleased to announce a recent partnership with Spire Federal integrating Xona capability into their GNSS simulators. And we're also, very pleased to be backed by our investors, such as Seraphim and Mac Ventures, who led our last round, along with others such as Toyota Ventures, 1517, Stellar Solution, and Trucks, among others. So we're very, very, very happy to be supported by such a great group of folks to sort of get this first demonstration satellite up in the air. And this first demonstration satellite really allows us to test major aspects of the system. So these are things like software reprogrammability on orbit to add new capability after the fact. But really, the primary goal is to show that such a payload that's suitable for a low Earth orbit small satellite deployment can generate signals of high quality for position, navigation, and timing as a service. And with that, I think this is my last slide. So I'll say thank you very much for your attention, and thank you again for the opportunity to speak here today and to the organizers. Very happy to take any questions or open things up for discussion, but I'll say feel free to reach out to my email as well if you're shy with your question here today or would like to dive in a bit more. It's Tyler@xonaspace.com in case it's been cut off at the bottom there, but yeah, thank you very much.
Well, thank you very much, Tyler. Fantastic presentation. So let's open the floor for questions. Anyone, just unmute.
I have a quick question. Can you hear me okay?
Go ahead, Julian.
Yeah, one of your slides you mentioned about penetration into buildings. Do you guys have some kind of like estimate for that? So like if we were to deploy this in say like a data center location, like how far into the building would we expect it to penetrate?
Yeah, great question. And this is exactly one of the things we intend to test in the demonstration satellite mission, but I'll say the analyses we've done so far really are targeting around penetration capability of up to 2 or 3 kind of concrete wall level sort of indoor penetration to give a sense of it. And of course, it depends a lot on the kind of circumstances of where the building is and what kind of materials the building is made out of. But I feel like that gets to many of the use cases. But yeah, happy to dive more detail into that if you have a specific location in mind, but that gives an idea at least.
Okay, great. Thank you.
Yeah, great question. Thank you.
I have a question, Tyler. This is a little bit like, let's say, more related to the type of the satellite. Let's say there are certainly challenges with LEO, like in terms of, let's say, make the speed that you have, like you going through a relative speed. I mean, and like the window basically that you have, like things are open, requires you then to have more satellites, and then basically there's more points of failures. The general question is like, if you had access to put this in MEO, would you do it, or this is like built based on LEO for the benefits, not necessarily the availability?
Yeah, no, that's a really great question. I think that there's a really great trade study that can be done sort of with all the, if you had the infinite budget, what would the trade study look like?
Exactly.
That's a really great question.
Dollar sign was not an issue.
Yeah, dollar sign was not an issue. Yeah, very, very great question. I think if the dollar sign is not an issue, you would go to a LEO deployment, and I'll sort of expand on that. But the reason being is that there are elements from a performance perspective that really bring you things that you can't get from a medium Earth orbit deployment. And one of the big things there is really the rapid geometry change. So as much as that has its challenges, it also brings its benefits because, for example, to get to that centimeter level positioning with traditional precise point positioning techniques can take tens of minutes to get kind of a PPP float position for those of you who are kind of familiar with that. But to do this from LEO, you can really get that down in kind of the minute or sub-minute kind of level convergence time. So really bringing high precision in a more robust way. You don't need sort of this dense local infrastructure on the ground to do that. So really putting the infrastructure on the space side. And another reason why you might opt to do things on the LEO side is that if you did have infinite budget, putting up many spares on orbit, it really leads to a more distributed system where, yes, there are more potential points of failure, but there's also more satellites out there as well, in the sense that there's a robustness and the strength of numbers aspect to the system also. So at least that's my perspective on it. At least I'm sure others may have one as well, but that's at least from a sort of first order. That's what I would say.
Wonderful, thank you. Any more question?
Yeah, I have one question because on one of the slides, can you hear me?
Yes.
Yeah, in one of the slides you shown that the targeted number of satellites is around 200 or something. Isn't that too many? Because once you get too many sources of signals, you may get some interference problems and other that will actually decrease the quality.
Yeah, very, very good question. I'll say that there can be diminishing returns with too many signals, certainly. The number of satellites we expect to have in view is fairly similar to GPS. So although we're talking about sort of 300 satellite deployment, it's still more of a kind of 15 to 20 satellite in view type system, which is very similar to kind of GPS type numbers. And so it's very much, I guess, the same principles that lead to GPS working kind of with that many satellites in view are the same that we can leverage in this case as well. So although there's 10 times more satellites, because we're much closer to Earth, the footprint of each satellite is also 10 times less. So the equation kind of balances out towards getting, although GPS has kind of 30 or so satellites in its constellation deployment, leading to kind of 15 satellites in view for your average user. In LEO, to get the same sort of level of satellite visibility, kind of 15 satellites in view, it is kind of a 300 satellite constellation. Hope that answers your question.
I have a question.
Sure.
So you published a few papers in ION.
Yes.
Maybe you can one of them seems interesting, like redoing GNSS from scratch. Can you please send the group these papers?
Absolutely. I'd be very happy to share some of those papers. In fact, I can put them on the screen here. If I kept them in here, I did. Very good. There's a few papers that might be of interest to the group here. One with SAE, one with IEEE, and one with the ION. With SAE, this was, I'm not sure but I think the ION one might be the most relevant to your comment there.
Yeah, but how I can download them? Do I have to have membership in ION or what?
Great question. This paper is available for free on our website. I'm happy to send you a link as well.
Put the link, please. If it's available on your website, put the link.
Will do.
Thank you very much.
Yeah, thank you.
Tyler, would you be interested to, let's say, work with the community on, let's say, a focus group or, let's say, a work stream or whatever, we can define the details of a open source GNSS receiver that, I mean, mainly it will start with Xona, but in general, like it has, let's say, it opens up basically what we can do further with this.
Yeah, I think we are in support of that, and we would love to explore that more.
Wonderful. Yeah. So we have someone raising their hand. Patrick, go ahead.
Hey, just a quick question, Tyler. I was just trying to understand, or it seemed to be an indication that your satellites are going to synchronize with the existing GNSS constellations, or is there a system whereby, in order to ensure all your satellites are aligned to one another time-wise, do they synchronize with each other? How do you ensure they're all providing very accurate time?
Yeah, excellent question. Thank you for that. There are two major inputs to this, also the end system, as part of sort of achieving that goal. GNSS is one input to the system. As you can imagine, it's above us, it's there, it's an available source of information. It only makes sense to include that just to improve the robustness of the system. And for early deployment, particularly for the demonstration satellites, GNSS will be an input to that system for sure. In the longer term, however, being GNSS independent is very much important to the concept of the system. And so the architecture of that is really using an interconnected satellite system. So really using inter-satellite links and ground-to-satellite links to basically disseminate that time information via kind of a two-way ranging technique via the system. So it's really leveraging the network as an element of the system to do that.
Great, thanks.
Yeah, great question.
Georgi.
Yeah, I have a question. It's less technical, it's more about the business model, but I assume it is being a private company, you're going to sell a service. So it's very different than what current GPS is. And even though the current GPS is free, we see GLONASS, Galileo, Baidu, and so on. So by, selling a service, I assume that there will be competitors and other companies that will come with similar solutions, because this space is vast and different countries might have different needs and so on and so on. Do you have competitors at this point of time?
Yeah, it's a very great question. Maybe I'll try to address the first part of the question, which is how do you compete with free, right? You know, GPS, GNSS is a free service provided to the public. How do you compete with that? And really what we are more similar to in terms of competing is with the high performance GNSS markets. And so there's already well-established markets for GNSS correction, so providing correction information to GNSS to improve precision. There's also other services out there to improve either resilience or security of position or timing information. And really what we're after is trying to provide a service that combines all of those elements, so resilience, accuracy, and also the kind of security element to that as well. So it's not trying to compete with the free parts of the system, but trying to compete with the well-established kind of GNSS enhancement sort of high performance sort of market that's out there. So that's maybe the first part of the question. The second part of the question, which is more around kind of what do the competitors look like in this space? Well, certainly there are other competing technologies, either terrestrially based or others out there. And they all have their different merits, and I think are going to be part of the kind of system of systems solutions towards getting really a PNT solution that is highly robust, because ultimately different things work well in different environments. So in the case of autonomous driving, for example, a LiDAR system based localization works very well underground and kind of tunnel environments in parking garages. GNSS, not so much. So there are challenges with that. So I think they will all have their kind of place in sort of creating this system of systems solution towards a robust kind of overall PNT strategy. But there are other direct competitors out there. So for example, Geely has been very public about creating a combined communication and navigation system to support autonomy and automotive, more with a focus on the Chinese market, but nonetheless there are others out there who are looking in this space, and so we're not the only ones, for sure.
Thanks.
Yeah, great question.
So one question, Tyler, is the constellation also communicating with each other, like a mesh or something, or
that's the end goal. That's right.
That's the end goal.
Yep.
Son, you wanted to add something? Son put in the comment something about a. Okay, yeah. So Son basically mentioned there used to be like Beijing Future Navigation Technology, which no longer is in operation and would fit basically as a competitor, would have fit as a competitor, let's say. So.
And yeah, certainly the different constellations from the different governments are always adding more capability and to support different users and use cases. And we're really trying to support the specific use cases we mentioned here, which at least from what we've seen, there's not plans to serve those specific needs from those constellations, but that's changing all the time. So yeah.
Any more question?
Yeah, if I may, Tyler, you mentioned that first you will roll out some sort of like a compatible antenna that basically can convert the Xona signals to GNSS compatible format. Would that mean that anyone basically with this extra antenna will be able to receive your data with a regular GNSS receiver on the other end?
That's the goal in the interim step. There will be some functionality that will be lost in the sense that there's going to be extra data, extra sort of information on the signal, which will be decoded internally to that kind of transceiver device, but just won't, by means of kind of the limitations of kind of the GNSS messages out there, just won't have a way of finding its way into the system. So there'll be a limited service sort of capable sort of getting to that, getting to the end user device, but still getting it up and running and getting many of the benefits there. But that's why in the long term, it's really to integrate the service directly to the receivers so that you can really get the full benefit of what can come even in the future as well. But want to still support folks who have devices fielded already.
Thank you.
And do you have any targeted KPIs for such antenna, like targeted the time delay or position precision?
We do, and
use this?
we do, and I'll say that varies quite a bit by use case, and we do have antenna specifications. I'd be very happy to share them with you offline if that's something that you're interested in diving more deeply into. Absolutely.
Okay, thanks.
Yeah, I'd like to add to that real quick. This is Jaime. We also have additional information on our indoor signal penetration capabilities. So if anybody wants more information on that, if you can email Tyler, we can certainly talk about providing that the details of that paper.
Yeah, and thank you, Jaime, for that. And one thing I'll add, just because I know we're kind of at time here, is that if anyone's interested in learning more, we do have a detailed signal ICD of kind of interface control document, which for those of you familiar with the kind of GPS ICD and the details of that, we do have that prepared for our demonstration mission. So if you're interested in learning more, we're happy to share that with you offline as well.
Awesome. So we are on top of the hour. Again, thank you very much, Dr. Tyler. So if you have any question, you see Dr. Tyler's email down there, and wish you the best, and looking forward working with you guys on let's say a work stream, or we'll see what we can do. Great.
Yeah, likewise, and thank you very much for the invitation, and thank you all for listening. Great questions. It's a really great discussion.
You're welcome. Okay, bye everyone.
Bye everyone. Thank you.
Bye.
Bye-bye.
Thanks.
Thank you.
All right, Ahmad, I'll go ahead and drop off. I just want to say thank you again.
Sure.
It's great
You're
to
welcome.
meet you.
You're very welcome.
Bye-bye.
Bye.
Hey, Ahmad.
Hey. So, can we stop the recording now? I don't want to press any button to lose the talk.
You won't lose it. It's showing that it recorded fine. So
Wonderful.
you can either end the call or you can stop the recording and then in the call. Either way is fine.
Yeah, I leave it to you.
Okay, sounds good.
Awesome. Okay. Bye, everyone.